welcome Professor Hehl.
Thank you very much. I'm impressed that still some people are here. I have to say that today, so far I brought these pictures and these analogies and the plausibility remarks and so on. Today I want to present the formalism of Poincaré gauge theory. And this, of course, is very demanding, and I don't expect that everybody can follow in detail the formalism I'm presenting to you. But it's in X-ray differential forms, but it gives a good structure, and I think to get some insight in the structure, and I will again give some exercises. There are still a student who does all the exercises, so he will then probably also understand the formalism. So in chapter 5, this is according to what is also in our book. We have general structure of Poincaré gauge theory. Poincaré gauge theory, and in particular, including quadratic Lagrangians, including, this is essential, including quadratic Lagrangians, because this is, as in each Young-Mills theory, the quadratic Lagrangians are characteristic for a gauge theory. Quadratic in the field strength, of course, like in Maxwell's theory, F square, in Young-Mills theory, F square, and here, of course, we have then torsion square plus curvature square. So these are quadratic Lagrangians, but here also a linear piece is possible in curvature, in contrast to usual gauge theories. In section 5.1, I just want to recapitulate the geometry, Riemann-Cartan space-time, well, RC, Riemann-Cartan space-time, as arena for Poincaré gauge theory, which I abbreviate by PG, is Poincaré gauge theory. Poincaré gauge theory, I forgot. Now, it means that physics is now taking place in this gravitational theory in the Riemann-Cartan space. We already discussed this in the context of Kibble's gauging. We found a translational potential. This was the code frame. That was for translations. This was theta alpha equals E alpha I times dxi if we expand it in a natural code frame. And these are 4 times 4 components. And we have the Lorentz rotations. So we have the connection, the Lorentz connection, and this is gamma alpha beta, it's a one form, equals gamma I alpha beta if we develop it again in a natural basis, dxi, summation over I, of course I, j, k are coordinate indices, alpha, beta are frame indices, and since it's a Lorentz rotation, it's minus gamma, beta, alpha. So it's anti-symmetric in alpha and beta if we choose an orthonormal frame. So, and this, here we have, this is anti-symmetric, so alpha, beta, 6 times 4, so we have 6 times 4 components. 4 plus 4 plus, 6 plus 4, 6 times 4. We also learned that we have a generalization of the Einstein elevator. We could call it Kibble's elevator. Kibble's elevator. That locally at one point we can always normalize that theta alpha becomes Kronecker alpha I times dxi, so it's becoming trivial, and gamma can be locally transformed to 0. In these special frames, locally at one point, this can be achieved. So that's all locally at one point. Locally at one point P. Then we have the metric G. If we feed in the metric the frame E alpha, comma E beta, we get G alpha beta, the components of the metric, and we choose them also normal. So, which I call O alpha beta, which is identical to diagonal whatever convention we choose. That shows here plus 1, minus 1, minus 1, minus 1. But you can also choose the other convention. Now we have we use the exterior calculus, so we have an exterior derivative. Exterior derivative, which it's anti-commutative, it denoted by D. Is equal partial I times dxi. It's a one form. And we have the exterior covariant derivative. If there are some indices, Lorentz indices to be differentiated, exterior covariant derivative. So for instance here, which is called with a capital D of psi. Suppose we have a matter field with some indices, n holonomic indices, psi. I symbolize them all collectively with a capital A, and this is by definition the exterior derivative. Plus, and then you have to covariantly differentiate the other indices, and so symbolically written it's plus gamma, the connection, alpha beta, I write it in this way, because that's the original definition of a connection, one index up, one index down. Only if you have a metric, you can lower this, raise this index, and then you get gamma alpha beta. This is already in application. Apply to the representation matrices of the Lorentz group. So depending on whether you have a spinor, a vector, or a tensor, so these representation matrices depend on our Lorentz transformation alpha beta. And have an index capital A and capital B, and here we have psi B. So if you have, for instance, a vector, this is just a Kronecker. So this is a covariant exterior derivative. It means that each index has to be differentiated in the conventional way with a connection and summed, and the convention is, as usual, upper indices go with plus and lower indices go with minus, and only n holonomic indices get differentiated. This is what is called the covariant exterior derivative, let me just remark in the book of Scouten, which is the standard book in tensor analysis, he has also an operator which he calls nabla, alpha, but here is the number 2. I'm not explaining that, I'm just telling this to people who use that book, that they know that he has also the covariant exterior derivative, but it's not the nabla with alpha, the components, but it's a special type where some torsion pieces are added, and he calls it, as far as I recollect, nabla with a number 2. It's sort of the second type of differentiation. Okay, then the characteristic feature, I mean, this is all we need to know. I mean, if gamma is antisymmetric, originally the connection is of course not antisymmetric, but we assume in a Riemann-Cartan space it's antisymmetric, and this is a consequence of that the non-metricity vanishes. Non-metricity vanishes. This is to say that the covariant derivative of the metric or the non-metricity is defined Q alpha beta is by definition conventionally minus sign minus covariant exterior derivative of the metric G alpha beta, and this is equal to 0 by assumption. This is what we call follows a Riemann-Cartan space. A Riemann-Cartan space as a Riemann-Cartan space has a metric and a connection, and but the metric is compatible with the connection. That is to say, the covariant exterior derivative. Now we have learned what the covariant exterior derivative is minus exterior derivative of G alpha beta, and now you have to differentiate the both indices. So these are lower indices, so if you get a minus times minus plus gamma alpha, say mu, times G mu beta plus gamma, now you differentiate the second index, beta mu times G alpha mu, and you can easily see, of course, that you lower the index, you get here alpha beta, here you get beta alpha, so that's nothing but minus B G alpha beta plus 2 times gamma alpha beta symmetric, right? The parenthesis is always 1/2 alpha beta minus beta alpha. And this is 0. Now since and this is for convenience, and which we want to get the Lorentz group manifest, so we choose G constant. So the anholonomic metric is a constant, and then the covariant derivative vanishes. And then, of course, as a consequence, you have that the symmetric part vanishes, or you can also write it that gamma alpha beta is equal minus gamma beta alpha. And that's what we assumed at the beginning. It's just in order to illustrate that this is a consequence of the vanishing non-metricity. So one has to be careful. I mean, the connection, the Lorentz connection is independent, but the linear connection gamma is of course a more general object, and the Lorentz connection is just the antisymmetric piece of this connection. And the particular one, namely this, which resides in a Riemann-Cartan space. So a Riemann-Cartan space is characterized by this vanishing non-metricity. So if you apply you can also see that on a more fundamental level, if you apply the Ricci lemma, to G alpha beta. You make two differentiation to G alpha beta. Then you get, this is minus E of Q alpha beta, by definition of the Q. And if you apply the Ricci lemma, then this is always curvature tensor times R with the first index plus with the second index. And if you evaluate this according to the Ricci lemma, you get just here 2 R alpha beta symmetric. This is no, there is a minus missing. Wait a minute. This is a minus here, and you get here also minus, and as a consequence you get here E Q alpha beta is equal to 2 times R alpha beta. We call that the zeroth Bianchi identity, because it is similar to the first and the second one, but it's sort of in a space where Q vanishes, R is automatically antisymmetric in these two. The curvature R, please note, R is the curvature, not the Ricci tensor as in index formalism. This is a full curvature 2 form, which we can really write now down. We have here the curvature 2 form. Now we have the variables. We have the coframe. We have the connection. Now we differentiate the coframe, that is the torsion, T alpha, by definition, covariant exterior derivative of the coframe is exterior derivative of the coframe. Index is gamma index plus gamma alpha mu h theta. This is the torsion. And of course the curvature curvature is similar. It's a curvature 2 form. This is a torsion 2 form. The field strengths are always 2 forms. Of course, theta is a 1 form and the covariant derivative is a 1 form, so this is a 2 form. Similar in the curvature tensor, you take the curl of the connection, you get R alpha beta in the Stauden conventions I'm using. This is D gamma alpha beta minus gamma alpha gamma, which capital gamma gamma beta. So this is also a 2 form, as you can see, because gamma is a 1 form and this is a 1 form. So that's a 2 form. So they are rich unit field strength. Now, we spoke already about the zeroth Bianchi identity. The first Bianchi identity is the identity for the torsion. And this is, of course, you can easily achieve. You just differentiate covariantly exterior the torsion. And you get here E of the torsion is equal. And then you get the theta, and this you can again evaluate by the Ricci lemma. Then you find here, this is theta beta, which are alpha beta. So that's the first Bianchi identity. I mean, these are just names which, for instance, first Bianchi identity you can find in the book of Spivak, for instance. I mean, historically they have nothing to do with Bianchi. Even in the second Bianchi identity, you do the same game for the curvature. dr alpha beta is equal to 0. You can differentiate that and can evaluate it. You will easily find out that it is 0. And this is called the second Bianchi identity. And this is what is usually called in Riemannian geometry Bianchi identity, which also was not found by Bianchi incidentally, but these are just names which are household names, and it's easy to use them, but they are not historically correct. Because torsion and non-electricity were found much after Bianchi. This was the identity where he was involved. The history or the original papers you can find in the book of Scouten. He's very careful in giving the right references. So this is what you know from general relativity, the Bianchi identity. You can, if you like, and which I'm not going to do, irreducibly decompose the Bianchi identities. So for instance, this Bianchi identity, you know, the curvature attention is a 2-form, so this is a 3-form. A 3-form has 4 different components times, and these are, because it's anti-symmetric and alpha beta 6 times 4 are 24 independent components, and you can irreducibly decompose. One of the irreducible pieces of the Bianchi identity is the one which you use in order to evaluate the energy momentum theorem, which you know from general relativity. Okay, so this is a little bit, now we have to use, of course, also integrals, so we have to define what is called a volume 4 form. Volume, I'm talking, of course, about 4-dimensional volumes. I mean, a 1-dimensional volume, a line is described by a 1 form, an area by a 2 form, a 3-dimensional by a 3 form, and a 4-dimensional volume, which we need for our integrals, is of course the 4 form. So, and this is called eta. We see calculus usually, and we define it, well, we know from general relativity the volume is related to the determinant of the matrix. So what we, in this definition, we have the square root of the modulus of the determinant of the metric, G is a mu. And to blow it up to a 4 form, we just take the frame theta 0, wedge theta 1, wedge theta 2, wedge theta 3. And in order to bring this in a different form, in order to be able to apply the usual definitions, we take the Levi-Civita symbol and rewrite it. It's 1/4 factorial times square root of this determinant, modulus of the determinant, and times epsilon 1, 2, 0, 1, 2, 3 times theta 1, which theta 0, 1, 2, 3. These are just, it's just rewritten, but here you can easily see the 4 form, and you have here the Levi-Civita. This is a permutation symbol, so the Levi-Civita. Permutation symbol. So it's plus or minus 0 or 1, depending on whether the indices are even or odd or no permutations of the numbers 0, 1, 2, 3. So you can also write it with a Hodge star, which is an operator. We use an operator which we call the star operator or Hodge operator, Hodge, which maps P forms into n minus P forms, into n or 4 minus P forms. They are in 4 dimensions. I mean, this depends on, I'm restricting myself this lecture to 4 dimensions, 4 minus P. So this can be written really as the Hodge operator applied to 1. The Hodge operator is always characterized by an epsilon which takes the plural of forms. So I'm not going into details. We have to use strictly in this physics application of exterior calculus, we have to introduce even forms and odd forms, or what is also called forms without twist and twisted forms. This is just a reminder of twisted forms. Twisted forms, the twisted form is distinguished from an untwisted form by the parity operation. It behaves differently under reflections. If you want a decent discussion, I already several times pointed out the book of Frankl, and the Hodge star is a twisted operator which makes out of a twisted form untwisted and vice versa. So we have as basis for our as basis for the forms, we have of course then the theta alpha basis. Well, we have of course a 1, then which is a 0 form, then a 1 form. Then we can always develop with respect to two forms. If we have theta alpha times theta beta, and theta alpha, theta beta, theta gamma is the 3 forms. Theta alpha, which theta beta, which theta gamma, which theta delta is a 4 form. So you have here a 0, 1, 2, 3, and 4 form. And you can always develop your quantities if you know their form character with respect to these spaces. So we call this the theta basis. In exterior calculus, it's very helpful to introduce also the eta basis. Now, what is the eta? The eta we already defined. We have eta, which is a 1 form. Then you have eta